everyone. My name is Karel Kubat. I'm the CEO of Union. We are an infrastructure company focused on zk-based bridging. Our initial stack is completely based around IBC, which is a technology originally from Cosmos that allows any chain to trustlessly connect to each other. We were founded about 8 months ago and have been focused on doing what should have been done a couple of years ago. Basically building infrastructure the way crypto is supposed to be used, completely around trustless technology, completely around censorship-resistant technology to avoid possible abuse by hackers, to avoid censorship by the US government or any nation state or company, and basically adhere to the original Bitcoin philosophy. For my talking points today, I'm going to keep it really high level and not dive too deep into the mathematics behind the zk stuff that we're doing. I think in the Rollup that's been discussed a couple of times already. Instead, we're going to focus very much on the fundamentals of trustless bridging, focusing on exactly what we're trying to accomplish and what the algorithm looks like from a very high level. I'm going to dive a little bit into why zk doesn't just improve this system from a security perspective and also allows for kind of new innovation to be built on top of this layer and kind of new applications. And then we're going to dive into what I like to refer to as the really cool delusionally tech stuff, which is centered around, for example, proof of proofs, which massively improves lifeline-based bridging altogether, and obfuscated messaging, which is about how do you keep bridging transfers completely private. This is a very big issue for protocols that are automatically trying to interact with bridges, let's say a lending protocol or a vault that invests on different chains, because as you can imagine, when you do bridging, you add massive latency from a technical perspective, 12-second latency, which allows a lot more MEV to be extracted. And so keeping these messages private is actually key to scaling automated messaging between chains. To understand the fundamentals of trustless bridging, we kind of need to understand what finalization is, Merkle proofs, and state verification. These are three core concepts that right now are 100% necessary to do this correctly. And basically every single chain supports this, every single modern chain. There's a couple of weird ones out there that, for example, don't store their state inside Merkle trees, which means that you can't really do header verification. I believe Stellar is one of those older chains from 2016 or 17 that doesn't do this. Some examples of protocols that are lifeline based are IBC, which I already mentioned, and telepathy by Succinct Labs. Telepathy is a bit of an outlier here because it focuses purely on consensus verification and kind of adds a message passing layer on top of that. But it's not really an infrastructure or a bridging protocol. It's also not what Succinct Labs does. They're mainly focused on consensus verification themselves. So the first really important concept to understand is finalization, which is basically the chain's process of ensuring that a block is never going to be reorged, or phrased differently, when I look at a certain transaction that comes into my wallet, when can I be sure that I really will keep that money? So for example, if I were to go to a store and pay with a credit card, at what point does the shopkeeper truly know that the transaction isn't going to be reverted? Because this is the moment that they can let me leave with my goods. For a credit card transfer, finalization happens in about 3 seconds. For Cosmos chains, finalization happens every 6 seconds because we have single slot finality. Every single block is always finalized. For Ethereum, this technically happens every 6.4 minutes times 2, because there's 2 rounds going on of checkpointing. And for Bitcoin itself, this technically never happens, but at some point you may be quite sure. We can differentiate 2 fundamental ways of doing finalization. One is for proof of work, where creating each subsequent block has a certain difficulty associated with it. And if we were to basically count up how much work has been spent on a certain block, we can see that for the 3rd block here, 20 units of work have been spent, which means that for this block to be reverted, someone will need to spend at least 21 units of work. Well, if 1 unit of work is $1,000, then for block number 3, you can be sure of $20,000 in value needs to be spent to try to reorganize this block. So for transfers that are below 20,000, you can basically safely accept them. Now with Bitcoin, obviously in proof of work, the value is much greater for one single unit of work. But this is actually the confirmations that you see when you do an exchange transfer. This is basically the amount of blocks that we wait for finalization. For proof of stake chains, there's a periodic checkpoint, and this checkpoint can happen every single block or every X block. So for Cosmos chains, it happens every single block. For Ethereum chains, it happens every, what is it? I don't know, every 100 blocks, let's say so, which involves the validators all doing a vote and basically putting a stake on checkpointing this block, which if it is reverted later on, they lose their stake. So now we have a mechanism for both chains to basically tie a certain value to knowing that the block is going to be final. And this value is key in being able to do a bridging transfer. Because a bridging transfer is very much similar, like the shopkeeper that needs to know that the transaction is going to be truly final. A bridge can really only send the funds to another chain once it knows that the deposit on the origin chain is never going to be reverted. So if we can tie some type of monetary value to knowing that's not going to be reverted, we can then have a risk model and say that there is a 0% risk or a very, very small risk associated with performing an attack for stealing funds from the bridge. The other key concept is Merkle proofs, which basically entails creating a tree-like data structure from the underlying data in the chain and being able to prove that some data is on the chain. Now, this is more a computer science concept, which as a regular user, you will probably never encounter. You might encounter this because it's a mechanism that's used a lot in airdrops, used as a Merkle distributor. Basically, the concept is that for the nodes in the Merkle tree, we create extra nodes in between, which are the hashes of the intermediate nodes. So, for example, A and B are hashed together, C and D are hashed together, and then finally the root of the tree is the hash of A, B, C, D. In this case, a Merkle tree allows us to generate Merkle inclusion proofs, which can be if I have only the root, the top block of the tree, which is a, let's say, 256 byte hash. We can then create a proof and say A is inside this blockchain by providing the data from B and the hash from C and D. And by hashing those together, we obtain the same state root, and that way we know that the data is present there. Now, for this tree in particular here, it's not a massive data saver. For those that are doing the calculations on paper by hand, you might notice that really what you avoid doing is transmitting one block of value. So instead of needing to provide A, B, C, and D, we only need to provide B and the hash of C and D, so just 2 blocks. Now, for much larger Merkle trees, this becomes a real data saver. And this is key to client-based bridging because we want to make a statement on what data is stored on the opposing chain. And so by doing a really cheap, small proof, we're paying a lot less gas for this inclusion. Imagine if you had to provide all of the data, A through D, or in case of Ethereum, the full state itself, you would need to send over gigabytes, if not hundreds of gigabytes of data to be able to prove that one single piece of data is present on that chain. Now, Merkle proofs are basically used everywhere in blockchain. It's, I think, one of the most fundamental data structures that we see used right now. If you look at a block itself, example here, it has a block header, which usually contains a state root, which is the Merkle tree root of the entire underlying state. So A through Z for basically every account storage slot. So that contains ERC20 balances, Uniswap pool data, bridging data, NFT data, ENS, etc. All of that is compressed into that single state root. For most chains, it contains a validator root, in the case of Cosmos chains, for example, which is all of the validator-related data into one single state root. Now, validator root is incredibly important for client-based bridging because if you have this root, you can make statements about who the current validators are and who the next validators are. And that's kind of key in the light client-based process. Other stuff that's included is the receipt route, which is all of the events emitted. And for other chains, there's a bunch of other routes associated with it. And then, of course, a block has a list of transactions. Usually there's a transaction route as well. And that way, with a single block header, you can make proofs about any single transaction that's inside the block without actually needing to forward all of those transactions to another chain. As an example, as a Litecoin-based bridge, the main question when you have a transfer from an origin chain to a destination chain is, am I allowed to mint tokens or am I allowed to release tokens? That's the question that the smart contract is asking. And for this, a smart contract accepts a certain type of proof. For trusted bridging, like Layer 0 or XLR or Wormhole, usually a group of validators or multi-sig participants create a proof, which is then signing that a transaction should be allowed. So in this case, the Litecoin proving mechanism is taken away, and instead we have a proof of authority. For trustless bridging, the mechanism works very differently. Assuming that we have the previous block header already on the chain, we can forward the next block header to the destination chain and use the validator route to obtain current data from the validators using Merkle inclusion proofs. By that, we can then show that this new block header is the new finalized header. So what we might, for example, show is that this new block header has been signed by 2/3 of all validators. In that case, the Litecoin smart contract will assume that this new provided block header is the next finalized block header itself. There's some extra bookkeeping that needs to be done here. For example, you check that the block height is greater. You check that a certain amount of time has passed. There's usually with live clients a whole host of rules regarding the protocol. So in the case of Ethereum, you don't just check for 2/3 of all validators, you check for a specific subset of validators called the signing committee, and you verify that the current signing committee has signed this, and then you can set what's going to be the next signing committee. After you've got the block header on a chain, you can then use the state route to show that on the origin chain, someone has interacted with the bridging contract, which usually entails doing a lockup of funds or a burn of funds. By doing a Merkle inclusion proof of the state route and showing that funds have been locked up, the smart contract can then make a statement and say, all right, on the origin chain, funds are definitely locked up with the intention of being sent to this chain. Hence, I'm allowed to unlock funds or to mint funds. And this, of course, for bridging protocols leads into profit because now we've bridged over funds and we can charge a BPS fee for that, or do it for free, as is more common in IBC. But in grand spectrum of things, now we've reached our success state. The way back goes exactly the same. We take the block headers from the destination chain and send them over to the origin chain and do the same proving mechanism. So in the end, all that Litecoins really do is track the finalization of a certain chain, have all of these rules about this chain embedded into them, and update what they consider to be the current header of a chain. Now, Litecoin-based bridging is a lot more complicated than doing trusted bridging because it involves handling the different types of consensus per chain, which can vary wildly out there. And it also entails upgrading them, as for example, an Ethereum hard fork to a new consensus basically leads to all dependent Litecoins need to be updated. It means that if there's an attack on a chain, the Litecoin needs to be able to detect this. And usually, especially the attack detection portion is what takes a lot of the effort in building this. Luckily for larger chains, attacks are really uncommon. For example, to attack a trustless bridge with Ethereum, you'd need to be able to control 2/3 of the validator set of Ethereum, which is not feasible at all. And if that's the case, then to be honest, bridge hacks are the least of our concerns. We would have a lot more concerns regarding all DeFi happening at that time. zk Light clients, which is what Union kind of specializes in our IBC stack, do this whole operation, but instead of having a monolithic light client contract in Solidity where we handle all of these checks, signature verifications, inclusion proofs, etc., we actually offload all of this computation to a circuit. We add some extra bookkeeping regarding our bridging system here as well, because circuit verification on-chain always has a constant cost, which means that the more computation we can offload, the cheaper the bridging transfers really become. Now, zk Light clients have a few issues with them. One of them is that signature verification is notoriously expensive to perform. The same goes for these Merkle inclusion proofs, because usually they use SHA-256, which is very zk unfriendly, which zk unfriendly just means takes a lot of effort to compute, which leads to longer proving times. In the end, we've now kind of reached a stage that zk Light clients are competitive with regular Light clients, especially in costs. So for example, right now for Union, doing a batch of transfers, which is infinite in size, but usually it's about 100 to 200 transfers, costs about $6 to verify in gas on Ethereum, which is kind of like the golden egg that we've been waiting for, the end-all solution to doing bridging correctly. Now, for this Light client, like I mentioned, we keep track of all validators, we keep track of consensus changes, we handle liveliness. This is a portion that's very difficult to keep track of as well. Liveliness is the property that the finalization keeps on going, or that the chain keeps producing blocks. Kind of depends on what you read online and how people define it. But we've seen it actually happen before in Ethereum, where the beacon chain halted. Luckily, execution kept continuing, but this means that Light client-based bridges end up being in a semi-broken state until the beacon chain is rebooted and starts producing blocks again. Right now for Ethereum, it's definitely a bit of a, I would say, experimental stage. I'm quite confident that we're not going to see a lot more issues with the beacon chain, but we'll see what actually happens in the future. Another issue is, of course, malicious validators, especially with large parties gaining a control of the validator set, such as Lido. The actual risk of a malicious validator set becomes greater. I'm not saying that Lido as a DAO is malicious, but if someone were to gain control of their oracles and their multi-sigs, they could use that to install a large set of validators on Ethereum and then try to do an attack to gain control of the network. And there's probably a host more attack vectors that you need to take into account. The great advantage with this is that instead of the attack vectors being Lazarus attempts to get the multi-sig that's being hosted by a single company, they need to attack the entirety of Ethereum. So very much the same way that EigenLayer as a security mechanism has the entire Ethereum validator set, so do zk Light clients, or Light clients in general, benefit from the entire validator set themselves, instead of from a smaller company subset that has a multi-sig. Now, I briefly mentioned state verification. That is a lot more experimental right now. State verification basically entails that not only do we build Light clients around verifying the validator root, we also run all of the transactions in a block in a zero-knowledge circuit. What this allows us to do is actually remove the complete trust dependency on validators for the correct execution of transactions. And instead, we just need them to finalize a block. Why is this important? Validators could, of course, not abide by the rules of the EVM. We've, of course, defined in the EVM that 1 + 1 = 2, but if 2/3 of the validators were to fork their nodes and make that 3, then the blockchain would still produce blocks, still continue to do stuff, but our bridging logic would be completely off, and we'd end up with unbacked tokens. Some really cool projects here right now include ZE by RiskZero, which can do state verification for Ethereum. The downside is that this is still relatively slow. On the top of my head, it takes about 17 minutes per Ethereum block to do verification, while for just regular Light client updates, it's closer to somewhere around a minute to 2 to do full verification. The benefit, of course, of this system already existing is that we can do fraud proofs with this. So the fast path for trustless bridging does not need to take state verification into account, but off-chain observers can do this. And in the case that they detect fraud happening, they can construct the slower to construct ZK proof and do the state verification there, and then allow the bridge to be paused, shut down, or for validators to be slashed. So some of the cooler stuff, because I think probably most of the listeners are quite aware of light client-based bridging. They allow us to do a lot more stuff as well besides just asset transfer. One of the applications I'm most bullish on that Union is working on a lot is shared security, which is basically, can you, for example, build a sovereign rollup or a Cosmos app chain or a substrate standalone chain and actually benefit from the eigenlayer security set? For this, you need a trustless connection between the two chains. You could use a header oracle. The downside is that then not only do you tie your application logic to the Oracle protocol that you're using, and so your DeFi is at risk, you're now also tying your consensus to the Oracle itself. Which means that if an Oracle attack happens, not only do certain protocols on your chain lose funds, you lose your entire chain. Hence why, if your objective is to increase the security of your chain, for shared security, you really want light client-based bridging. Storage proofs, really cool application as well. Longhash has today just published an article on the application of IBC with storage proofs. What this entails is using the headers that you have on the chain and the Merkle inclusion proofs associated with the state roots to create historic proofs for a chain. So for example, the number of trades that have occurred on Uniswap since inception, or the cumulative amount of impermanent loss on Uniswap. Of course, you could try to record this with a TWEB oracle, but the downside is TWEBs can be manipulated, plus they are relatively inaccurate. Now with storage proofs, you actually get the data as is. So it's true data from Genesis until now, compressed into a single small proof. And so if you were to build an app chain that has a low block time for options trading, you could still do a light client-based connection to Ethereum and get high quality price data from Ethereum without needing to use a Chainlink oracle, without needing to use a trusted bridging provider. And that way basically create your really nice end user application while benefiting from the larger ecosystem. Another big one is that light client-based bridges can be completely permissionless, especially if you add state verification to the feature set. Permissionless isn't just that users can choose to use this bridge without being censored. It also means that you can boot up a new chain or a rollup and connect to the IBC network without needing to do a governance proposal, without needing to talk to the Union team, basically the same way as creating a server and connecting to the internet. You don't need to actually go through a 3-month process to open up your bridging channels or find a bridging partner. Now, this is actually what got me into bridging initially. This idea that I want to see a future where we have thousands of chains, thousands of rollups and execution environments, even for every single bank, every single financial institution, and actually be able to connect them all to each other without needing to go through a long process. As I already mentioned, censorship resistance, in the case of IBC and of Union, even if Union Labs would want to take this whole system down, that would be impossible. People can still produce their own ZK proofs. On my M2, it takes about 2 minutes. On a more production-like server, 4 to 5 seconds, which means that it's truly decentralized. So it's not a security. You do not need to ban US citizens from using the system. You can ban them. You cannot ban them at all from using the system. And in the case that anyone would want to take it down, you couldn't. So as a protocol using this, you're also not vendor locked in. You're not going to get worked at some point or be tied to tokens from a bridge protocol that has failed, and now all of your liquidity is in Nomad USDC. And these benefits, to be honest, is why we're in crypto, to really make sure that we are completely self-sovereign. Now, proof of proofs kind of goes into like the more delusional stuff for the techies. So once you start building out these light client-based connections and you start booting up all of these chains, you start to realize that you create this very dense network where For example, blockchain B is connected to D, E, F, A, and C, which means that you're creating individual proofs for all of these networks, sending them to all of these networks, and you're doing that for each one. So as you start adding more networks here, obviously the computational overhead starts increasing, as well as the verification overhead. So for blockchain E to stay up to date here, basically it needs to allocate block space to do verification for D, A, B, C, and F, which means that now we're spending 90% of our block space on doing zk proof verification, which is not ideal because block space is expensive. Plus, we want to save as much block space for end users. At the same time, E loves to be connected to all chains because we want to give our end users really great UX when they do bridging, and we want to connect with as many protocols out there. We want to get as much TVL into this chain, as much different financial assets. A solution to this is what's referred to as the proof of proofs, where we create a super zk proof that contains light client data for all chains connected to the network. Now, the computation still stays the same as connecting every single chain, but the verification has a constant block space, even if you start adding new chains to the set. So basically, if we add chain X to this bunch, instead of connecting directly to every single chain, we compress the proof, aggregate it in the single proof of proof, and submit that to every single chain. And now you've got kind of this one ultimate layer of bridging where you can make statements about any chain connected to the wider network. The downside of this technology at the moment is that for proof of proofs, you need to do a lot of computation, plus you lose the constant size zk proofs that you otherwise would benefit from. So this is still, I think, about 2 to 3 years away from actually becoming a reality. But when it does, we kind of have the ultimate solution. Also offers some great benefits, because if you have this single kind of entry point for bridging across all chains, allows you to do coincident ones, it allows you to do integrations with off-chain or private chain order flow, and it allows you to basically do better intent routing. Instead of users specifying that they want to go from A to B and then to E, you can basically route the intent to this proof of proofs and then settle that atomically across all chains. And finally, a tidbit that we've been experimenting on together with Quasar is obfuscated messaging. So a lot of cross-chain messaging happens by protocols. For example, Squid Router, Sommelier, Quasar, they use bridges to communicate objectives to their outposts on different chains. So for example, perform a trade on this DEX and send the funds back to my chain, or perform a trade and send it to a third chain, an LP. Now, these messages are relatively simple in the execution, but the problem is, since their chain itself is the calculator for these strategies, they basically show their hand. An MEV searcher can observe their origin chain and realize what their rebalancing strategy is going to be and try to extract as much MEV from this rebalance. Now, ideally, what you want is to actually obfuscate the strategy and the messaging, such that an MEV searcher cannot know at all what the actual strategy is performed by the chain. To do obfuscated messaging, we basically need to do a few different technologies. First of all, on a chain like Quasar, we do our strategy calculation using a circuit as well. That way we can keep the strategy a secret until it's actually enacted. Obviously, if we were to still do the strategy in public on Quasar, but then send out all the messages privately, you could still kind of deduce what's going on and extract MEV. So a strategist does the calculation, creates a new strategy. The strategy goes to the circuit, the verifier, and if it passes the verification, it produces a set of transaction hashes, or a set of message hashes that need to be sent to different chains. This is what we refer to as a pre-image, by the way. Instead of actually settling this directly on Ethereum, we can settle these transaction hashes using proposer builder separation, or for now by using flashbots. That way we can already ensure that the transaction itself is going to be included in Ethereum without actually showing what the data contents are going to be. Now, once the block is actually produced, the content of the strategy needs to be shown. But in this case, it's no longer front runnable. So you end up with a system where, in the end, the chain still verify that these strategies are completely valid and by the rules set by Quasar, but you're able to include them in blocks on other chains without ever having an MEV search and know what's going on. Oh, I just mentioned this. So by sending the transaction hash to PBS directly, you basically get the transaction included without making it front runnable at all. This is kind of what's going to be, I think, the cutting edge of cross-chain strategies. So far, we've already seen Sommelier climb to, I think, the number 10 or number 9 yield aggregator on Ethereum within the last 3 months. And the whole reason that we see cross-chain DeFi performing better than regular on-chain DeFi is that we're offloading computation away from Ethereum and to its own separate co-processor chain, which makes the ability to do much more complex strategies feasible. So that's why Quasar or Sommelier can actually outperform, let's say, Yearn, simply because they can do much more computation on their strategy. And as we see trustless bridging grow and the yield opportunities on other chains become more available, these cross-chain strategies are only going to become more competitive, especially with these obfuscated messages that allow them to do really any strategy that a regular trader would be allowed to do as well. So I think we're going to go to the Q&A now. For those interested in what we're doing, check out union.build on our website or on Twitter. And feel free to give me a follow. I regularly tweet about this stuff and link research articles. I'm also always interested in discussing more tech with people, so feel free to reach out with DMs to me.
Thanks so much. That was awesome. It's super cool to see from your perspective, basically, with the zk background, some of the answers to the questions that I've been trying to answer myself. In this last week, I've been doing a lot of just research and on cross Rollup communication, and recently just put out a post about whether or not we need bridges in the future, where we're headed. It was an interesting one, and there's tons of different points there. But yeah, I will pass the first question over to Rob, unless he doesn't have one, because I've got tons. And I will take the back seat as I went first last time.
I appreciate that. Yeah, I think we totally align on this vision of thousands and thousands of rollups and interoperability across those chains. I think you laid out a very clear picture of how those chains could connect. I do have questions, but I'm also curious about the point that Andy brings up about whether or not bridges are necessary with respect to crossing between these chains, whether it's transfers or if it's data going back and forth between these chains. So I'll kind of pose that as the first question. Are bridges necessary when we have thousands of rollups?
So I think bridges as we have right now are going to become unnecessary. Those committee-based or multi-sig-based services aren't going to be necessary within the ecosystem. What I do think that we've seen is that initially rollups were seen as a scaling strategy for Ethereum itself. And over the last year, we've kind of seen rollups go a lot more sovereign. And we've seen with decentralized sequencer networks, with fork choice rules, really rollups being their own separate entities that just don't require a large validator set, but are separate entities from Ethereum itself and not just for scaling Ethereum. And using these new network stacks that we're seeing, you basically create what bridges do right now, but using a much more solid network stack. And that's actually why Union decided to invest mainly in IBC, because as a protocol, IBC itself can also encapsulate these new network stacks and provide a way where indeed you don't have one single trusted bridging protocol, but you do have a protocol for different rollup technologies to communicate, for different decentralized sequencer networks to communicate. And the great thing then, of course, is what if this protocol also can do L1s, right? What if you just have this single layer of interoperability? And think that's, at least for me as a dev that wants to use this stuff, the biggest gripe right now. I hate having to use 4 different bridging services to get the correct assets on a single chain to LP.
Yeah, it's interesting take. Yeah, we came to some consensuses, or some consensus as well with regards to a similar kind of outlook, and I'll share that with you. I have 2 questions. One in particular to the slides, and then also one in particular based on the slides and what you guys are building with bringing IBC and Ethereum together. But first, with the slides, there's 2 parts in the slides here. And I think I can actually push back, which is super cool. So this part, obfuscated messaging, and then the zk zk light clients, right? So being able to basically do obfuscated messaging using zk light clients or zk technology with cross-chain messaging or bridging. Is this a world where we get a more private DeFi experience? Is that what you guys are building towards? Is that what this is enabling by kind of using zk? Or am I kind of missing the bigger picture as to why this is being built, or to kind of what the tech enables?
Yeah, so we start out by using zk just for the scaling itself. Doing light clients with just regular Solidity would be 3 to 6 million gas per light client update. With zk, it's basically 200K. So it's just a necessity to make the system actually feasible. From that moment on, you obviously start realizing, now that you're doing stuff in zk anyway, that you have a lot more potential to do additional features on top, which is where this obfuscated messaging comes in. Right now, actually Squid Router does a lot of traffic overall, and integrates, I think, with like 40 different DEXs, which you can only see the MEV opportunity by monitoring what's going to happen with a transaction that gets routed over 3 chains and interacts with 3 different DEXs on those chains. A sophisticated MEV extractor that plays all 3 chains will basically always ensure worst possible execution for you when you arrive at your destination. If we don't want to go to this world of worst possible execution always, then we do need a system that does privacy for us. I think it's a big mistake that people make right now. They think privacy is about avoiding paying taxes, dealing with stolen money, but that's not the case at all. Privacy is about getting best possible execution on your DeFi. And that's why like protocols like Anoma and such doing private intents are so important.
Yeah, very cool. Yeah, that seems like more like a feature enabled by the tech, right? Which is awesome. I think there's an you just keep going. The IBC Ethereum endgame is I think it's definitely worth it to touch on now, but I've just got so many more questions too. So you guys just went on your testnet, basically enabling IBC and Ethereum, quote unquote, the endgame. That is enabled through this technology, which we spoke about today, and other various technologies. So yeah, what is the state of the IBC and Ethereum interoperability, and how did the technology that you talked about today, or how does the technology you talked about today, how is that going to impact this IBC and Ethereum connection, and kind of where you guys aiming to be?
Yeah, so where's the technology right now? We were hoping to actually launch transfers to over testnet on Monday or Tuesday. So keep your ears open for that. Most of the work we're doing right now is actually making the RPCs a little bit more production ready, so that when we launch this, we're not going to go offline half an hour later. What is this going to enable? So right now with these trusted bridging protocols, the ecosystems around them, although they are like growing, they're very much centered around each protocol themselves. Instead of with IBC, where we have parties like Skip, TFM, 42, etc., all working independently on top of the same protocol. By bringing IBC to Ethereum, you immediately connect every single Cosmos chain, every single Polkadot chain, as well as you allow all these teams to independently continue building their products, right? So that's this like all important shared interface that we have. It's kind of the same thing that allowed Ethereum to grow, right? Like the EVM is a shared interface for protocols to independently build whatever they want without like needing to sit down. Right? You just check what the API is and you integrate with it. And IBC kind of brings that same potential for new products to be built to cross-chain bridging and messaging, because you just have this one open standard without needing to go sit down with a certain team. You can just do your full integration and build your company on top. I think what we're going to see next is IBC to Rollups, what I've alluded to, enter new L1s. And so what's the case for Union here? We're looking to take a market position on this fundamental tech, but the success of IBC isn't tied to the success of Union. It's been growing very steadily over the last 3 years. It's doing still massive transfer volume, and the tech itself is, to be honest, tremendously improving every month with the storage proofs changes, ICQ, etc. So I'm very bullish on this whole area, kind of being ready for the next bull market to take the dominant position as trustless technology over Chainlink's CCIP network. I think those are kind of going to be two opposing factors, one being fully decentralized, one being centered around a single company.
I think it's a really compelling model that you lay out, and one that I think the next bull market, we all kind of like feel it coming, but I don't know if it would actually happen without some of this technology. Because if we don't have this interop across rollups in this world where there's thousands of chains, I think the user experience is quite lacking, because there's no normies that are going to bridge themselves across 4 or 5 different modular chains. With an interop solution like this, I think it is possible to put all of that in the back end and provide users a nice, easy user experience that can hopefully lead to lots of adoption and a flood of users entering the ecosystem again, like we saw in 2017 and then in 2020. I think this solution is really, really critical, and I'm curious about the integration workflow. For any protocols that are watching this or hear about Union, is there integration work that they can do ahead of time? Is it simply a matter of pointing to a different RPC? Like what is the integration workflow?
Yeah, so our public testnet is launching in a couple of weeks. So then basically they get the ability to do all integrations they want. The workflow really is only on-chain. It's contracts that handle sending messages, sending transfers, reading state, doing storage proofs, as well as doing the refunds. So in the case of IBC, you cannot have tokens be locked up in limbo. You either get them back or they arrive on the other chain, but there's never an in-between state. So really, it's very much designed from the perspective, I'm a smart contract inside a sandbox. I cannot like integrate with an outside world or issue a ticket on Discord or whatever. Kind of use case wise, like what you started out with talking about, what we've seen so far interest wise is as well the lower bridging risk. I think myself for the next bull market, it's not even called big players to be honest, but there's plenty of players out there that have 100 million, 200 million, 300 million of STETH or other assets that want to earn additional yield on it, that have taken that from their clients, smaller users, etc., that currently can't really bridge that over or do too much with it, simply because we've seen the 100th bridge get hacked. The risk profile is just too great. But now with this trustless technology, I do think we're actually going to reach the era where the risk is acceptable enough that we actually can make these assets do something useful, which is a massive opportunity for protocols on rollups, on AppChain specifically, DYDX, V4, etc., to actually take on a lot of this TVL. So I'm thinking once the system is live, we're going to see more institutional players do, not for them large transfers, but for the DeFi space itself, definitely large transfers.
Awesome. Quick like follow-up as to how I understand that from the perspective of like someone who might recognize this and is leading, a network or an ecosystem. A lot of times, like to get from chain A to chain B, it takes 3 or 4 hops. And this could provide a direct hop from chain A to chain B. And that's before we open up to the world of app chains and thousands of rollups. Connecting with a direct hop from one chain to another chain, I think is a small scale problem now, and it's only going to become a bigger and bigger problem. And Union, here's the solution.
And there's facilities here to handle all of it. So even if it's technically multiple hops, there's basically virtual channels. If you go more into the IBC specification, etc. So for the developers building out and integrating, it still seems like a single hop that occurs where the tokens can't be stuck on one of the intermediate chains. So either reaches the end or it's reverted and back on the origin chain. You can do batch asset transfers together with general message passing. So instead of first sending out your assets, waiting for them to arrive, then sending an additional message to do something with that, all of that can be compressed into a single one. So there's a lot of really cool applications, I think, that can open up on this. And the moment you no longer need to use two different bridging providers, you remove the dependency of basically needing to check every single time, like where the fuck did my assets arrive on, which I have wrote like a couple of smart contracts doing asset transfers across chains. You do need to check a lot. Where the fuck is this going wrong?
Yeah. I think, and we could talk, at length about this. I think there's like a dilemma that's been put forth where it's a trade-off between scalability. If you're choosing to launch an app chain or your own Rollup, sovereign or not sovereign, you can choose scalability, but you trade off composability with the rest of the on-chain world. But it doesn't sound like with this technology, you have to make that decision. It seems like with this technology, you can choose scalability in an app chain and then also stay composable with the rest of Ethereum and the rest of modular rollups.
Yeah, and that's the exact objective, right? Like I want to see a DeFi summer of applications that don't live on one specific chain. I want users to kind of stop thinking about I'm an Avalanche user and I do Avalanche DeFi. I just want them to like Trader Joe, Star Arena, FriendTech, Uniswap, and just have those be on their bookmarks and just be transferring in between them without really realizing what chains they are being backed by. And that's what's going to be, I think, the next bull market.
Yeah, that's it. I mean, that's the way that, like if you think about Web 2 apps, like you don't think about, what browser you're using or what type of info or email server you're on, or, you just use it. You just use the social media app. You just use the financial app, the game or whatever it is. So yeah, I think the shift between from the fat protocol thesis basically is still correct in terms of like the value accrual mechanism for like say Ethereum due to all these apps and different chains and rollups and all these different things happening and all this just basically social capital. However, the real 0 to 1 for crypto adoption, in my opinion, is what you say, where this UX of these apps that people use and have really no care where.
Yeah, and at least for me, like I don't even think it's social capital or first to market advantage. I think it's just UX advantage. If it takes me 30 minutes to figure out how to go to a new rollup and do something with it, then I kind of need like a 20% APY plus to actually be willing to do these operations. And I think that's why like Ethereum and some of the first to markets have an advantage, because you're just not going to take the effort to move to a new ecosystem. If I need to go through Medium posts with 40 screenshots on how to connect my new wallets and do all these steps, I just can't be bothered. And so with like this new technology, like you said, for new startups building their products, you can now choose to truly create the experience that you want tailored for your end users, instead of having to choose a inferior solution simply because you need to provide easier access.
Yeah, no doubt. I think that's a great spot to kind of wrap up and push forward with the idea of what's possible in the future. Thank you so much, Carol, for coming on and giving us a badass presentation about what you guys are building. And yeah, thanks for the time.
Thank you very much, guys.
Thanks, Carol. This was fun.